So in this video, we're going to be covering AVL trees. If you have not subscribed to the channel, hit the subscribe button and like this video, or watch the video and then like it. It helps us out a lot. If you want to support us, go to the backtobacksuite.com website. We're hosting a growing service and I'll talk about it at the end, but let's get into the lesson first. In this video, we're going to be looking at AVL trees. Now, we've looked at binary search trees before. We know that they have the property. If we look in the left subtree, we're going to have items less. If we look in the right subtree, we're going to have items greater than or equal to. Sometimes I've seen it less than or equal to and then greater. All that AVL trees add on to that is we're going to have a self-balancing property to them. And they're going to balance themselves after we do inserts and after we do deletes. And why do we want to do that? Remember that if we have a binary search tree, let's say we were inserting 3, 2, and 1. That is skewed to the left, we see. So that's going to be linear if we were trying to search because we have 3 nodes and we're going to have to search all of those nodes. We could go as deep as that last node. The whole thing that we're trying to avoid is that skewedness. And if we balance our tree and define certain thresholds on the balance we have at each node, we can keep these searches logarithmic. And that's what we want to do. So that's what we want. We're going to talk about balance. We're going to review what balance is. We're going to look at rotation. Where are these rotation operations? We're going to look at left rotations, right rotations, left to right, and right left. And then we're going to be doing an implementation of insertion. In the interest of time, we're just going to do insertion. It's going to be a good bit of code. So I just realized that's not a binary search tree. Let me fix that. Going back to that property, we know that our left subtree is less than, and then that right subtree is greater than or equal to. And what we're going to do is we're going to have a rebalancing threshold. And we're going to look at the balance at every node in the tree. If we break a certain threshold in standard AVL trees, that's going to be 1. We're going to need to rebalance. I keep talking about balance, thresholds. Let's actually look at the idea of balance first, and then we'll get into our rotations. So now balance. Remember, we always talk about trees in a recursive manner. We have this node n, and this node is going to have a left subtree and a right subtree. They're both going to be recursively defined. So every single node roots its own subtree. We think about it recursively. And if we were thinking in terms of a function, we would have a function, and then we would have that node as a parameter to the function and do something with the left and right subtrees. We need to define a height. What is the height of a subtree? So if we have nothing, if we just have a null node, we're going to say that the height is -1. We could call it height 0. It could be either, as long as we stay consistent. So we have a height of -1. And I sometimes like to say it's underwater. If we just have a null node, it's like we're underneath the tree. That's just kind of how I remember it. I have a little fish swimming there. And then if we have a single node, we're going to have a height of 0. So in this case, if we just have a single node, that's height 0. And then as soon as we start adding nodes on, we need to have a recursive definition for this height. So we're going to say, let me find the height out of this left subtree. And remember, this guy up here, that node n wants to know the height of his subtree. The way he's going to get his height is he needs to look at the left subtree he owns and the right subtree. We're going to look at the left subtree right there. We're going to look at the right subtree right here. We're going to see between these guys, who has the larger height? And then we're going to add 1 to that. So then there we go. That's going to give us the height. And we're going to see more examples of this as we continue on. So that is height. If we have nothing, it's going to be -1. If we have a single node, it's going to be 0. If we have more than a single node, we're going to need a recursive definition. Now, what does balance at a specific node mean? Balance is going to be the height of the left subtree minus the height of the right subtree. That is going to give us the balance at a certain node n. And so what an AVL tree does is it's going to keep this balance, the absolute value of this balance, within a certain threshold. And here we see it can be parameterized. So AVL trees are going to have a threshold of 1. We can make that threshold more, but the standard threshold is going to be 1. So that's what we're going to see in our examples. Now let's do some examples and start calculating some balance. I've kept these two things up here, our balance equation and how our threshold is going to be 1. We're going to start at the root node. What is the balance of that node 3? So we have the balance of 3. We need to look at the left subtree. So do you see this tree right there? That is a whole tree to itself. And we need to consider what the height of that is. So we see a single node at the root. So that's a height of 0, as we defined before. And then we have a left subtree which is just a single node. We have a right subtree, which is just a single node. Ultimately, the height of that left subtree becomes just 1. And so the height of that left subtree is 1. And now what is the height of the right subtree? That's going to be this guy. We see that it's a single node. And since it's a single node, we know that's height 0. And then once we evaluate this, we're just going to get 1. So, okay, now this is 1. And what was our threshold? Our threshold is 1. Look at this threshold right there. 1 is less than or equal to 1. 1 is equal to 1. We know that the balance at that top node is 1. So let's just make note of that. Okay, so we just calculated the balance at the root node. The balance is 1. And I want you to notice something. This is left heavy. So I want you to notice, look at the equation. If we have a positive balance, that means that that left side of the equation, that guy right there, is dominating and he's going to bring us positive. That means we're left heavy. If we're right heavy, our balance is going to be negative. This guy over here is going to dominate our equation. That is something to just pay attention to. That's going to be a part of our pattern matching later. It'll make it really easy to internalize our rotations later. So now we can continue on. We can calculate the balance for this guy right here. What is the balance for him? So we're going to say, what is the height of his left subtree? minus 1. What is the height of his right subtree? minus 1. And then 1 minus 1 minus minus 1, that's just going to be 0. So the balance at 4 is 0. Okay, so now let's look at the 1. Let's calculate the balance over there. He has a left subtree single node. What is a single node? Height 0. And then we need to find the right subtree height. We need to find the height of that guy right there. His height is 0. He's just a single node. So 0 minus 0 is 0. So that means that the height at this 1 is going to be 0, or the balance is going to be 0. And so if we continue on, we're going to see that the balance of this 0 here is just 0. He has a minus 1 left, minus 1 right. That's just going to become 0. Same thing for that guy right here. So we're just going to make those 0. So we can see that this tree is special. We have a balance of 1, balance of 0, balance of 0, balance of 0, a balance of 0. All of those are within our balance parameter. We want to stay within a balance of 1. So the absolute value of any of those will be less than or equal to 1. This is an AVL tree. It is adhered to our threshold. All of the balances check out, and there's nothing we need to do here. This tree is balanced. We're going to have logarithmic search. Now let's look at a tree that might not adhere to this property. So let's look at this tree. Okay, so we have a tree right here. Let's start at the 4 and let's find the balance out of 4. We're going to need the left subtree minus the right subtree, and that's going to give us our balance. The right subtree of 4, let's do that very quickly. It's empty, so just minus 1. So the left subtree has a height of 0, and then we have 1 and then 2. So then we can just eyeball this and we can see that the height is 2. We could do the math, but we can see that we have a single node, which is 0, 1, and then that is 2 minus this minus 1, 2 plus 1 equals 3. We see that instantly. At our root node, we have broken the property, and this is not an AVL tree. So this is not an AVL tree. And this brings us to rotations. Rotations are how we're going to maintain, we're going to maintain the binary search tree invariant at the same time as maintaining this balance threshold right here. Let's look at what rotations are, and specifically, what are they trying to achieve? When we're talking about rotations, we could start out with abstract subtrees, and that can get confusing if you're not used to the notation. I want to just start off with some pattern recognition and just kind of build up a intuitive sense of what should we do when a tree looks a certain way. Although in reality, you would look at the math. We'll look at the implementation, but I think this is a good way to step into this first, and then we'll go to the concrete implementation and it'll become very straightforward. Rotations fix imbalance in our tree. Basically what we're doing, we're trying to move nodes over to the other side of the tree that needs nodes. If we're left heavy, we want to go to the right. If we're right heavy, we want to move nodes to the left. And there's specific ways we have to do this. So specifically, if we're left heavy, we're going to do a right rotation, or a left rotation and then a right rotation. We would call it a left-right rotation. And we're going to see exactly what these look like. No worry about that. If we're right heavy, we're going to throw nodes over to the left. We can do a left rotation, or we'll do a right rotation first and then a left. And we'll see these two guys are confusing at first. These are confusing until we see examples of what they look like. Here we see a right rotation. So this guy is a right rotation. And I want you to notice the tree on the left up here, it could be left heavy, and we're trying to move nodes to the right subtree. The key thing I want you to notice is there's always two nodes in a tango whenever we are doing these rotations. Two nodes are going to be critical, and then all of the other subtrees are going to dance around, and they're going to maintain that binary search tree invariant as we move these two critical nodes. Notice those X and Y's. Those are the nodes we're going to care about. And notice the special properties we're maintaining doing this right rotation. And these will be clear as we do examples. There's a node X and there's a node Y. We know that Y is less than X. Let's just write some things we know. Y is less than X. So we see this little red triangle. What do we know about that red triangle? We know that that red triangle is less than Y and less than X. Okay, we're just going off what we know. We're not taking any, we're not doing any abstract rotations. We're not making abstract subtrees. We're just looking at what the tree is telling us. And this is a really good way to reason about data structure problems. Let's look at this blue triangle. This blue triangle is greater than Y, greater than or equal to Y, and it's going to be less than X. That blue triangle fits that property. This purple triangle will be greater than or equal to Y, and it will be greater than or equal to X. What we do here is we want to move these nodes to the right. We're going to turn Y and we're going to push Y up to where X is. And then we're going to bring X down and move it to become the right child of this Y, which has just become the root of this new tree. Forget about all of these subtrees. Forget about those subtrees down there. Before we do anything, I just want you to notice whenever we're doing rotations, just move the Y and the X. So the Y is going to move to the root, the X is going to move down. Now we need to know where do the subtrees fall in place so that we maintain the binary search tree invariant and we don't lose any nodes. We don't want to lose any nodes. Let's look at the properties that we had before. So we see that this subtree right here, the red one, less than Y, less than X. Over here, this subtree right there, that makes sense. That's also less than Y and less than X. So that holds. So then let's look at this blue subtree right here. So this guy is greater than or equal to Y and less than X. And yeah, that makes sense. We went greater than or equal to Y, and then we went less than X. So everything's checking out. So now this purple subtree right there, we're going to go greater than or equal to Y. Great, we did that. And then greater than or equal to X. So we did the same thing. And guess what we just did? We just performed a rotation of these two elements, and we kept all of these subtrees. We maintained their positioning and their ordering. So this is still a binary search tree, and we have fixed the balance. Now that we've seen a rotation in action, let's look at all of the specific rotations so that we can get a better feel for them. So remember, order matters when we're doing insertions on binary search trees. We're going to perform these insertions. Every single time we perform an insertion, we're going to be checking to make sure we didn't break balance at any node, break this threshold property. Okay, so let's insert 3. Okay, we inserted 3. We're going to insert 2. If we insert 2, we're going to want to go to the left. So let's insert 2. So we just inserted 2. This is still a binary search tree. All of the balances check out, and we could recalculate them, but for the sake of time, I'm just going to, you can do that in your head. We'll just continue with this demonstration. Now we're going to need to insert the 1. So we're going to go to the left, and then we're going to go to the left. But there's a problem. And so the more of these that you do, you're just going to be able to see it. I don't want to do the math at every node. Eventually, you're just going to be able to see whether there's an imbalance. But in reality, if you were coding this, you would want to know concretely. We're going to be recursively, after this node gets inserted, the call stack will return to this function call. He's going to check his balance. Then he returns. He's going to check his balance. That's how it would actually be implemented. But for the sake of just speed, we're just not going to trace it as the code would do it. We're going to just talk it through. The root is imbalanced. We have the right is -1. And then the left is going to be a depth of 1. So this leads to a 2. So this is bad. We just broke the property. And so what rotation can we use? Notice what our balance is. Our balance is 2. And remember, since our balance is 2, the left subtree is dominating. We are left heavy. So what does that mean? We can do a right rotation. Get those nodes out of the left subtree, move them to the right. And so there's a catch to this. We'll see that when we get to the left-right rotation, which is next. So remember, when we do the rotation, only focus on X and Y. Only focus on 2 nodes. We're going to move this 2 up. We're going to move the 3 down. We need to fix the subtrees. Remember, there's actually 3 subtrees going on here. We're going to have this subtree, we're going to have this subtree, and we're going to have that subtree. What do we do with those? So first off, these guys don't even exist. So they're not even in the picture. The code would have to handle them if they were populated. But this 1, where does that 1 go? Well, we know 1 is less than this y. We know 1 is less than this x. So this 1 can just go here. This is less than y, less than x. So we've maintained our property. So that is the right rotation completed. Notice how we started out. We just rotated these guys. Just worry about x and y. Just rotate the nodes that matter and then adjust the subtrees. We saw that this subtree gets adjusted. That is the right rotation. Take these guys, move them to the right. We're rotating to the right. Left heavy, we fixed the left heavy by moving to the right. So now let's look at a different situation where we're left heavy, but we can't just do the right rotation. So now we're at a left right rotation. Let's do this. Let's insert the 3, then we insert the 1. We can eyeball this. We still see that we're balanced, and then we insert the 2. We're left heavy. If we calculate the balance at the root node, which is where balance is broken, we're going to see that we have -1 in the right subtree, and then we're going to see we have a balance of 1 in the left. So again, we have a balance of 2. Can we just do the right rotation? We're going to try that. Let's just try doing the right rotation. Pull the 1 up, push the 3 down. That is the right rotation started, and then the 2 is going to have to go right there. Because it's greater than 1 and less than 3, it's greater than 1 and less than 3, it's greater than 1 and less than 3. But this is not balanced. If we look at the root has a -1, minus, if we look at the right, this has a balance of 1. This is -2. This is not balanced. This breaks the AVL property. So we can't just do a right rotation here. There's something different we have to do. This is where we would do something called a left-right rotation. We're going to take these 2 guys right here. These 2 guys, we're going to do a left rotation. And then once we do a left rotation there, we're going to do a right rotation on the subsequent nodes. So first, let's do a left rotation. So we're going to pop over the 2, pop over the 1. So we did a left rotation there, and the 3 is just going to be up here. Now we've performed the left rotation. Right there, that's the left rotation. And so now we need to perform the right rotation up here. So we're going to do the right rotation. So now we're going to push the 2 up and then the 3 down, and then the 1 goes here. So this is it. This is the final tree, and this is a balanced binary search tree within our threshold. So that's left to right. Both of these are left heavy restorations. Now that we understand how these rotations are done, or at least we saw initial examples, we can look at how we fix right heaviness, and it's just the opposite. It's the same operations. So now let's insert 1, let's insert 2, and then let's insert 3. We see we have a problem, and now we can do a left rotation. So we're going to bring the 2 up, we're going to bring the 1 down. So remember, these are our nodes we're focusing on, and we're moving to the left. So that 1 moves to the left, because it's a left rotation. And then this 3 just goes right there. And then this is our finished binary search tree. So choose the root, left, right, and that is the tree. So that's our left rotation. And then let's look at right, left. So insert a 1. We're going to insert a 3, and then we're going to insert a 2. And this is when the balance is broken. But again, if we just do a left rotation, what happens? We're going to see 3. We're going to have a 1 there. And then the 2 is greater than 1, less than 3, greater than 1, less than 3. Then the 2 is going to go here. And again, this is not an AVL tree. So we need to do something different. We're going to first do the right rotation. We're going to do the right rotation. So it's going to become 1, 2, 3. And then we're going to do a left rotation. So it becomes 2, 1, 3. And then that is an AVL tree. This might be confusing at first. This might not, you might not get it at first, but if you do a few examples, do a couple practice problems on this, it's going to become very, very intuitive how these rotations happen. So that's all we're going to cover for this video. If you want to see the full implementation, you can go to backtobacksui.com. We have a growing service. We are working very hard on it. In the past month, we have released, I think, 4 programming languages. We've released Java. We've released C#. We released C# 2 days ago. We released Python. We released JavaScript. We're going to release C++ in a week. We're going to be releasing Swift, Golang, maybe Ruby soon, maybe in the next month. And we have a ton of great things we want to build. We've put the infrastructure in place to scale. Right now we have about 130 or so problems. We want to create 300 problems, 500 high signal problems. And that's what we want to do with our service. So the best way that you can support us is to go to backtobacksui.com. The link is in the description. So that is all.